So in this video, we are going to look at how electron structure influences periodic trends in covalent radius, ionization energy, and ionic radius. These are all important properties in terms of determining bond strength and the energy relationships associated with forming chemical bonds. We'll look at covalent radius first. So this is really a measure of the size of an atom. It's formally defined as 1/2 the distance between the nuclei in a molecule consisting of two identical atoms joined by a covalent bond. And the length of a bond is correlated with the strength of that bond. So the shorter a bond, generally, the stronger the bond and the more potential energy that is stored within it. So covalent radius is ultimately a function of the size of the atoms that are bound together. And as a general trend, on the periodic table, when you go down a column, you'll find that the atoms tend to get bigger. And that means that the covalent radius gets bigger as well. This makes sense in terms of electron structure because as you go down a column on the periodic table, the valence electrons are found in higher and higher energy levels. So for example, these are simple Bohr model depictions of elements from column 2 of the periodic table. And as we go down, you can see that for each of these elements, we increase the number of core electrons. And so our two valence electrons are consistently farther and farther away from that nucleus. So we have larger and larger atoms. Okay, so as we go down a column on the periodic table, we increase the number of electrons and we increase the size of the atoms. But this is not what we see when we go across a row on the periodic table. The trend here is in the opposite direction. Atoms are actually larger in general at the beginning of a row than they are at the end. And I've drawn the arrow here pointing to the side of the periodic table that will have generally larger atoms. Now this doesn't make sense because as we go across a row on the periodic table, our atomic numbers are getting bigger, which means that the number of electrons are increasing and the masses are getting bigger. So these are getting heavier. Why are they getting smaller? Now remember that the mass of the nucleus ultimately just reflects the influence of the protons and the neutrons, not the electrons. And those protons and neutrons are packed inside that dense nucleus. So an increase in the mass doesn't necessarily influence the overall volume because it's the electrons that really define the space that an atom will really occupy, the overall size. And there is a critical difference in the way electrons are added to an atom as you go across a row compared to down a column. As we go across a row, those additional electrons are all added to the same valence shell, to the same outer energy level. And that means that they're all getting added to a shell that's approximately the same distance from the nucleus. And that explains why we're not seeing a large increase in atomic radius as we go across a row, but it doesn't necessarily explain why we actually see things getting smaller as we add more electrons. And that has to do with what's going on inside that nucleus. So as you go across a row, you are also increasing the positive charge of that nucleus because you're adding protons. And the positive charge of the nucleus is what is essentially attracting those outer electrons. And so if you increase that positive charge, those outer electrons are being drawn in more effectively at the far right of the row, where we have higher nuclear charges, than they are at the far left of the row, where we have lower nuclear charges. As a result, atoms tend to be smaller as you go across from left to right a row on the periodic table. So another way of explaining this is that the core electrons actually screen or shield those outer valence electrons from the full nuclear charge. And if you increase the number of core electrons, you'll increase the shielding and more effectively screen those valence electrons from feeling the full pull of the nucleus. So this is a picture of a lithium atom, and you can see the two core electrons in the 1s2 shell, and the valence, the outer electron, in the 2s shell. Now, the full nuclear charge of this lithium atom is +3 for the 3 protons that are present. But what this outer electron actually feels is not that full +3 charge. Because of these intervening core electrons, it's actually shielded or screened from that full nuclear charge. And we say that its effective nuclear charge, it's not exactly 1, it's approximately 1. But it's a lot less than what that number of protons might indicate. So in general, core electrons help screen or shield valence electrons from that nuclear charge. Now let's look at a little more precise numbers for shielding effect and effective nuclear charge as we go across the second row of the periodic table and the third row. And notice in particular what a large difference in shielding effect we have for elements that are in the same column on the periodic table, just a little bit farther down. So between lithium and sodium in column 1, we've increased the number of core electrons significantly. And as a result, the shielding effect really jumps to a large degree between the two. And that large increase in shielding effect means that the actual effective nuclear charge of these two atoms, so the pull felt by those outer valence electrons, is actually not that significantly different. You'll also notice that as we go across a row on the periodic table, the shielding effect does increase a little bit. So those outer valence electrons, as we continue to add to them, they will contribute a little bit to shielding, but it's nowhere near as large of an influence as the core electrons have. So you will see the shielding effect increase, but it's not as effective in influencing that nuclear charge, the effective nuclear charge, and so that increases a lot more as you go across a row than it does when you go down a column. The second trend that we want to look at is ionization energy. And this is just the energy that's required to remove an electron from an atom. So the general trends for ionization energy are the exact opposite of what we see for covalent radius. So ionization energy tends to decrease as you go down a column. I show the arrow pointing to the elements that we expect to have higher ionization energies. And ionization energy also tends to increase as you go across a row. In general, the smaller an atom, the more tightly the outer electrons are held by the nucleus, and the more energy is required to remove one of those electrons. Sometimes you'll hear about successive ionization energies, and so these are just the energy that's required to remove additional electrons past the first electron from an atom. So when you hear the term first ionization energy, that's just the energy required to remove that first outer electron. A second ionization energy is the energy required to remove the second one. Third ionization is the third. Fourth ionization is for the fourth electron, and so forth. Now what you'll notice for every single one of the elements that are represented here is that the first ionization energy is always the lowest. As you continue to remove electrons from any atom, it will require more and more energy. What's also represented here is that general trend as we go across a row on the periodic table. So these are the elements from the third row. And you'll see that sodium, which is in column 1 on the far left, is the lowest ionization energy. So this is also the largest of the atoms in the third row. The highest ionization energy is associated with argon on the far right, and this is also the smallest of the atoms on the third row. But the last piece that I want to point out to you is associated with this zigzag highlighted in yellow here. It's there to note a large difference in each column between the two yellow highlighted blocks. So notice for sodium, for example, the ionization energy between the first and second jumps by 1,000-fold. We see a similar large increase between the second ionization energy and the third ionization energy for magnesium. And that increase keeps getting further and further down in terms of your successive ionization energies for each of these elements as we go across a row on the periodic table. What this zigzag line really represents, though, is the difference in energy between removing a valence electron versus a core electron. Above this yellow line, these are all valence electrons. These are all the ones in that outer energy level. And in general, those are just easier to remove than the core electrons. Once you've removed all of your valence electrons and you're left with just your core electrons and start pulling those, it's going to require a lot more energy. So the last trend we want to look at is ionic radius. And these are patterns in the size of an ion, in particular compared to its parent atom. And you'll see two opposing trends depending upon the type of ion that you're dealing with. For cations, the radius of the ion is always smaller than the neutral parent atom. And this makes sense because when you form a cation, you're removing electrons. And you're removing the valence electrons, so essentially you're removing that outer energy level of that atom. Now, in contrast, when an anion is formed, you're adding electrons, you're gaining electrons. And what you'll find is that the radius of an anion will always be larger than the neutral parent atom due to those gained electrons. In summary, covalent atomic radius will increase down a column from top to bottom, but decrease from left to right across a row of the periodic table. Ionization energy trends in the opposite direction to atomic radius. It will decrease down a column from top to bottom, but it increases from left to right across a row of the periodic table. And finally, cations are always smaller than their parent atom, and anions are always larger than their parent atom.